Welcome to another edition of Math for No Reason. In this edition, we are going to compute this integral. So the first task will be to see and to what function does it convert, and subsequently we will try to evaluate this limit. Let us define a sequence of functions. The first one is f0x, and that is identically 0 on this interval 0 to 4. f1x is root over x, and we will write this as root over x plus f0x. Now observe that f2x is root over x plus root x, and we can write this as square root of x plus f1x. Similarly, f3x can be written as square root of x plus f2x. So in general, we can write fn plus 1x as square root of x plus fnx. This is a key observation. Now, observe that f1x is greater than 0, or rather greater than equal to 0 for all x in the interval 0 to 4. And if you look at f2x, that is, as we have just seen, is square root of x plus f1x, and since f1x is greater than or equal to 0, you see that this is greater than or equal to root x, and root x is f1x. So f2x is greater than or equal to f1x. Similarly, if you look at f3x, that is square root of x plus f2x, and we have, since f1x is greater than or equal to 0 for all x in the interval 0 to 4, we also get that f2x is greater than f1x. So f3x is greater than or equal to f2x. Now, by induction, we can prove that fn plus 1x is greater than or equal to fn, and this is true for all n equal to 0, 1, 2. So we see that fnx is an increasing sequence for every value of x in the interval 0 to 4. An important point to note that we will work with. So this real numbers fnx is non-decreasing for every x where x lies in the interval 0 to 4. Now we claim that fnx is also bounded. So we guess a bound. We see that f1x is square root of x, and the maximum value is 2, but we can be more liberal and make it 4, and that is for all x in the interval. Now, if we go to f2x, so that is root over x plus root x, if this is less than equal to root over x plus 4, so therefore this is less than equal to 4 for all x in this range. And by induction, we can show that fnx is also less than equal to 4 for all n. So we find that the sequence fnx for every x in the interval 0 less than equal to x less than equal to 4 is bounded above by 4. Now, if a non-decreasing sequence of real numbers is bounded above, then it converges to a limit. We can assert that limit n goes to infinity fnx exists. So what is this limit? Now let us call this limit phi of x. Now if we use this relation, so fn plus 1x is equal to square root of x plus fnx, this will give us fn plus 1 square x is equal to x plus fn. By taking limits on both sides, we get this interesting relationship that the limit function must satisfy phi square x is equal to x plus phi x. Now let us use this to obtain the limit. It's a simple quadratic equation, so we will try to solve this quadratic equation to obtain phi x. Rewriting the equation, we have phi square x minus phi x minus x is equal to 0, and let phi x be called y. Then we have y square minus y minus x is equal to 0, and we know that the solution of this equation is, so this implies phi x is 1 plus minus root over 1 plus 4x divided by 2. But since x lies between 0 and 4, is 1 minus root over 1 plus 4x by 2 is negative, and since the sequence is always non-negative, the limit of a non-negative sequence cannot be negative. So we can conclude that phi x has to be 1 plus root over 1 plus 4x by. So we have been able to explicitly obtain a form for this. We can write as integral of 0 to 4 half minus phi x whole square dx, where phi x is 1 plus square root of 1 plus 4x by. Now our job becomes easy. Now let's look at half minus phi x whole square, and that gives us 1 by 4 minus phi x plus phi square. So since phi square minus phi x is equal to x, so this becomes 1 by 4 plus x. So half minus phi x square is equal to 1 by 4 plus x. So this is the very interesting result that we have obtained, that half minus phi x square is 1 by 4 plus x. So therefore, the given integral is integral 0 to 4 1 by 4 plus x dx, and now simple integration 1 by 4x plus x square by 2, which is equal to 9. So the integral is equal to 9. Thank you.